All right, last class, we were learning about classifying matter. We talked about things as pure substances, which can either be elements, they're on the periodic table, or compounds, which is a mixture of multiple elements on the periodic table, combined together in fixed ratios, and they're chemically bonded together. So the atoms are stuck to each other, they're not leaving each other. We also talked about mixtures, which can be either heterogeneous, meaning you don't have a smooth consistency throughout. So like thinking of things that you would have to shake up before you use them, like a vinaigrette salad dressing, or homogeneous mixtures that are smooth all the way through, same nice even consistency regardless of where you sample from, or where you taste from, or drink from. There are also some other distinguishing factors of matter, physical and chemical properties being two of those. So two types of properties. The physical properties can be displayed without changing its identity. So you can think of these as a change of form. We're just changing the way that it's presented. We're not changing anything about the chemical or the material, the matter itself. So for example, the characteristic odor of gasoline, the way that gas smells, hopefully you're not smelling it too much. It does smell nice though. So that smell of gasoline, when you smell the gasoline, it doesn't turn into something else, fortunately. It's still gasoline. You haven't ruined your tank of gas by smelling it. Other things like taste, color, appearance, melting point, and density are also physical properties. You can observe them without it changing into something else. Chemical properties are displayed only through changing identity. So in order to observe a chemical property, it becomes something else, a different chemical. So the flammability of gasoline being an example. When you light your gas on fire, driving your vehicle, running a lawnmower, burning it for fun, very controlled and safe manner. Don't do that a lot. When you're burning gasoline, in order for you to display or observe that it burns, you have to burn it. And when you burn it, it turns into something that's not gasoline anymore. So that would be a chemical property. Other things like corrosiveness, acidity, toxicity, typically also chemical properties. In order for you to observe something being toxic, usually it has to change into something else. It has to interact with something in your body that causes an adverse reaction, and it changes the chemical in the process. So some physical properties, things like the melting point of water is a physical property. The substance doesn't change. So if we're melting this ice in this little glass, when it melts from liquid ice to solid ice, it's still water. The solid ice was water. The liquid ice is water. Water before and water after. Which sounds like instructions for taking care of a plant. Chemical properties, on the other hand, the flammability of candle wax, it's the wax that's burning when you're burning a candle. The flammability of candle wax is a chemical property. The wax is burned. It's no longer wax. There might be a little bit of wax still that's floating around your house, but for the most part, the wax is being burned. It's being turned into other things. You're releasing energy from the bonds that are in the wax to form heat and light. So some things that we might expect, we don't know how to expect these yet, but we might expect some carbon dioxide to be produced. We might expect water to be produced. And there's probably some other things in there, especially if you see a little bit of smoke. That's a good indication that it's not a complete combustion. And we've got some other things being formed. The wax is going away, it's turning into something else entirely. And so that's a chemical property, it's flammability. So each of these, let's think about whether these are physical or chemical properties. To observe these properties, you have to turn into something new. Or can it be the same chemical before and after? The explosiveness of hydrogen gas. In order to observe hydrogen exploding, does it have to turn into something else?
Yes.
Yeah, it does. So this would be a chemical property. What about the bronze color of copper? To observe the bronze color of copper, does the copper turn into something else? No, it's still copper before and after. So that would be a physical property. It's a characteristic property of bronze. What about the shiny appearance of shiny silver? That would also be a physical property. When you look at a mirror and you observe, wow, that's so shiny, look at that weirdo standing on the other side. When you observe that, the mirror doesn't shatter into a million pieces because we don't have really bad breath like in SpongeBob. It's still a mirror, it's still there, it's still shiny. It doesn't turn into something else when we observe that it's reflective. What about the ability of dry ice to sublime, to change from a solid to a gas? That's also physical. It's still dry, it's still carbon dioxide. Dry ice is just carbon dioxide. We're just changing it from a solid directly into a gas. Questions about any of those? Correlating or relating to those properties, we also have changes that are also named physical and chemical. In a physical change, same chemical before and after. It just looks different. So it's related to our physical properties. When we observe a physical property, nothing has changed. When we observe a physical change, it's still the same chemical before and after. So melting would be the physical change that goes along with the physical property of the melting point. In a chemical change, matter does change its composition. So we get new chemicals. They're probably not the first time those things have been made, but they're different from what we had before. So for example, when we got the Statue of Liberty, we being the United States, and they put it up, over on that island, originally it was not green. The Statue of Liberty is made of copper. That copper turns green upon continued exposure to air, especially with all that salt water, that sea salt water. And that reacts with it to make that green color. One of the nice things about copper is that oxidative property, that process of changing it from the nice copper to the green copper, that doesn't continue like it does with some other metals. But that's just a fun fact. So copper turning green, copper is not normally green, so turning green is an indication that it went through a chemical change. Turned into a copper oxide. We incorporated oxygen in there. Okay, so physical changes. One thing that's always a physical change are state changes or phase changes, just another name for state changes. So anytime that you're changing between states of matter, that's always going to be a physical change. So if you're melting something, if you're freezing something, if you're boiling something, if you're condensing something, if you're subliming something, if you're depositing, vapor depositioning something, those are always going to be physical changes. It's the same chemical, you've just changed the way that the matter is arranged. A physical change just results in a different form of the same substance. So an example, other examples, like flattening a penny on a railroad track, which I think is something that you're not supposed to do. Probably bad for the trains. They probably don't like it. Pulling copper into wire. Things like that. You're just changing the way that it looks. It's kind of like Transformers. When they transform, it's still Bumblebee. It just looks sort of like a man instead of looking like a car. Those are physical changes. Chemical changes, on the other hand, atoms, molecules, the way that the matter is arranged is changing. Chemical changes result in new, and by new we mean different, substances. And we're going to talk a lot about chemical changes, particularly in the form of chemical reactions in the class. The things that we had before are the reactants. So the way that we'll typically see chemical reactions listed out is we'll have chemical reactants on the left side. The reactants react. That's what we have before the reaction. And then we've got the arrow that represents the reaction. Sometimes there's information above and below the arrow. We're not going to encounter that in this class, at least not very much, but sometimes you might see that. And then the things that are produced, the things that are on the right side, are the products. And this is what is produced. Surprise, surprise. What we're left with at the end. I will often interchangeably talk about these in terms of the left side, the reactant side, and the right side, the product side. You should know them as reactants and products, however. Questions so far? We're cruising. All right, some examples of physical changes. The big one, changing between states of matter. Also, separation of a mixture. So separating sand and water, or if you accidentally, what would be some things that you might spill? Maybe if you, for some reason, added your sugar to your salt container or your salt to your sugar container, and then you were able to magically sort them out, that would be very difficult to do at home. You haven't changed anything, it's still salt, it's still sugar, but now they're back in the containers that they're supposed to be. Other sort of physical changes like cutting, denting, stretching, so like flattening a penny, making a quarter into a ring, things like that. Breaking your chopsticks at a Chinese, Japanese, Thai, Vietnamese, or other restaurant that uses chopsticks, and making solutions, some solutions, so like dissolving sugar in water. There are other types of compounds that we're going to be learning about in Chapter 3, like table salt, sodium chloride, that when they're dissolved, they actually break into different pieces. And so they're different in solution when they're dissolved versus when they're not dissolved, when they're a solid. Sugar, when you dissolve it into solution, stays intact as sugar pieces, sugar molecules. So sometimes when we dissolve things, it's a physical change. Some examples of chemical changes and indicators. So some signs of chemical changes. A color change. The characteristic color of copper turning from bronzy, brown, to green, like with the Statue of Liberty, is an example of a color change. If light is produced, that's also a good sign that there's a chemical change. So burning things. Also temperature change, like burning things. Bubbles or gas being formed, but not from boiling, because boiling is a physical change. If there's a change in the smell or the taste. So if you're cooking and your dish is tasting pretty good, and then you cook it too far and it tastes very not good, that would be an example of a chemical change. You've burnt it. Solids forming from mixing two clear liquids, also an example of some signs of a chemical change. Questions, desires for examples? All right, let's think of these and see if we can come up with whether they're physical or chemical changes. We've got boiling water Is boiling water a physical or chemical change? Physical. Good participation. Physical. It's water before we boiled it. It's water after we boiled it. It's just the gas form. That would be an example of a state change. State changes are always physical changes. What about a nail, like when you'd hammer into a wall or a piece of wood? Rusting. Chemical. Some signs of that. The color usually changes. The texture changes. It's not the steel that we might love. It's now rust, which we are scared of. What about a green solution and a colorless solution being mixed, and the resulting mixture is a pale green color? I would say that this is probably a physical change. There isn't really a color change because it's going from green to pale green. We probably just diluted the solution. Probably physical. All right, two colorless solutions mixed. The resulting mixture has a yellow solid. Physical or chemical? Chemical. We've got a color change that indicates that it was a chemical change, and solid forming from clear liquids. That's this last point, solid forming from mixing two clear liquids. Question?
Just diluting something just is with like the act of diluting something, would that be a physical change, or would that?
Diluting would probably be a physical change, yeah. There is sometimes temperature change associated with diluting things or with mixing things together. It's not always. It might actually be because of a chemical change happening if there's a temperature change. If there's not a temperature change, like diluting normal things, it's probably just physical. All right, some ways that we can separate mixtures. One physical change that we can do to separate out mixtures is distillation. So this is an example of a distillation apparatus. The same sort of distillation that like stills from Prohibition when alcohol was illegal. And people still do this, even though alcohol is not illegal. This is an example, though, of separating out salt and water. So you would have some sort of a heat source, and you've got your mixture in this flask, the things that you're trying to separate. And we're applying heat so that we can get one of the two components to leave. In this case, we're going to be getting the water to leave. So we're going to heat this up until the water evaporates. We've got a thermometer up in here just to check on the temperature. It's sealed at the top, and so the water, when it turns into a gas, tries to go somewhere, and that somewhere that it goes is down through this condensing tube. In this condensing tube, we've got cold water in pumping from below, and then warm water pumping out from above. So we've got a tube that our gas can flow through, and then on the outside of that, we've got what's called a water jacket. So there's another tube outside of that. So we've got cold water running around the outside, and the vapor runs into that, the cold walls of the container, our condensing tube, and it turns back into liquid water and then collects down here in this receiving flask, and pressure is relieved through this little hose barb that's on the end of that. This is typically how essential oils are distilled, so you can also do something similar to this where you take like orange peel and put it in water, and then you can get the essential oils of the orange peel to condense into the receiving flask and leave most of the water behind. You can also do it with alcohol, but I think that's illegal, so don't do it. So that's one example of ways that you can separate things. Another way that you can separate mixtures is with filtration. So we've got a funnel with filter paper, and we're pouring a slurry, maybe water and like charcoal or some dark substance through, and the filter is going to catch the solid. And the liquid goes through. We have talked previously about the conservation of mass, the law of conservation of mass. Matter is neither created nor destroyed, and this applies to chemical reactions as well. One exception to this is nuclear reactions. Nuclear reactions, significant changes in mass occur. We're not going to talk about nuclear reactions until way towards the end of the class, and then we're not really going to be focused on the change in mass. In normal chemical reactions, though, the changes in mass, there are small changes in mass, are really small, and we can just generally ignore them. They're not noticeable with the equipment that we're using. So generally, during physical and chemical changes, the total amount of matter remains constant. Right, so the amount of grams of substance that we have remains constant. We saw that with Antoine Lavoisier, however you pronounce it, that French name. The guy that was burning stuff in the closed container. He trapped the smoke, and so the mass of the container didn't change. Normally when you burn something, you lose the smoke, so the mass does change. So for example, a type of question that we could have about this, let's say that we burn 32 grams of methane, which has the chemical formula CH4, on our gas stove. It will react with 64 grams of oxygen, which has the chemical formula O2. These are our two reactants, because it says react with. And then to form, meaning that's where we'd put our arrow in. And then we've got the mass of carbon dioxide, CO2 gas, that would be formed, and 36 grams of water, H2O, that would also be formed. And so we end up with the mass being 160 grams on the left side and 160 grams on the right side. The amount of mass that we started with is the same as the amount of mass that we ended with. We've just rearranged the way that the matter is ordered, the way that the elements, the atoms, are structured. Mass before equals mass after the reaction. All right, so let's try applying that with a problem that's similar but not exactly the same. Potassium hydroxide, which has the chemical formula KOH, readily reacts with carbon dioxide, CO2, to produce potassium carbonate and water. These are the chemical formulas. How many grams of potassium carbonate are produced if this many grams of KOH reacts with this many grams of CO2? The reaction also produces 36 grams of water. So the important part, well, one of the important parts, right, we're given a bunch of information. We're told chemicals. Potassium hydroxide reacts with carbon dioxide. We've got some keywords. To produce. That signals our reaction arrow. So everything after this is products. Our products are potassium carbonate and water. So we can start by writing out what's our reactants, what goes on the left side, our arrow in the middle, and what goes on the right side. So the two things that react, we've got potassium hydroxide. We'll just copy in the shorthand for it, KOH. And then to separate our reactants, we put a plus. And we've also got carbon dioxide, CO2. This is just visually laying out what goes on the left side, what goes on the right side, and then we can set up a little bit of algebra. So those are our reactants, our left side. We'll put in our arrow, and then our potassium carbonate is K2CO3, a plus to separate our products. Our other product is H2O. Questions about how we're setting this up? All right, and then we're given the grams of each of them. So we're going to take these grams and just put them underneath each of these chemical formulas. So for the KOH, 224.4 grams. For the CO2, 88.0 grams. And for the arrow, we're going to replace this with an equal sign. The amount of mass, the amount of matter that we have before has to equal the amount of mass or matter that we have after. So this is our starting mass. And the reaction produces 36.0 grams of water. We want to know how much K2CO3 is produced. So we're going to put in an X for that, because that's what we're trying to find. So what we can do to move our 36 grams to the left side, subtract both sides by 36 grams. So our X is on the right, and it's 224.4 grams plus 88.0 grams minus 36.0 grams. So we just tell our calculator to do that for us. Thank you, calculator. And X, the amount of grams of K2CO3 or potassium carbonate, is 276.4 grams. Questions? You could also just like change all of the names and symbols to whatever you want for now. So like you could decide that KOH, potassium hydroxide, you just want to put in A for that. We would just have A. Okay, how much of A do we have? 224.4 grams. Okay, how much of B do we have? Carbon dioxide is our B. B is 88.0 grams. H2O, we'll just call that C, 36 grams of C. The identity doesn't matter for now. We'll learn about when the identity and the reaction part matters soon. Questions at all? Okay. Density, which we're doing in lab this week. We got to it. So the density of a subject, of a substance, is the ratio of mass to volume. D equals M over V, where D is density, M is mass, V is volume. Can somebody give me an example of a unit of mass? Huh? Liters is not mass. Liters is volume. So liters would be an example of units for volume. What would be an example of a unit of mass? Grams. Or kilograms and liters, or milliliters, or equivalent to milliliters but different units, cubic centimeters. So we're looking for basically the metric version of weight on top. It's not exactly, but that, and then some unit of volume, which is cubic feet, cubic centimeters, cubic yards, liters, milliliters, something like that. Density is a fundamental property of substances, meaning that if the density of two things is the same, they could be the same substance if some of the other properties match up. So for example, like precious metals, gold, platinum, iridium are always going to have the same density. Wood typically has the same density for types of woods, and changing size doesn't change density. We can calculate density using the formula. So density equals mass over volume. So example, we've got a sample of liquid. It's got a volume of 22.5 milliliters and a mass of 27.2 grams. We want to calculate the density. For us, this is one step. Which number are we putting on top? Yeah, 27.2. That's the one that's the mass. And we're going to put that over 22.5 milliliters. Do any of our units cancel out? No, we've got grams on top, milliliters on the bottom. Those are different units, and so we just keep both of them. So we're going to plug into our calculator 27.2 divided by 22.5. Calculator says 1.208, and that 8 looks like it repeats forever. We'd round this to 1.21 for 3 significant figures. The craziest writing I've ever done. And then the units didn't cancel, and so they just come on through. So we've got grams per, meaning over, milliliters. And that's a typical unit for density. A common unit for density. Units. So it's just plug it into the formula, pull the units through. Let's say that a person buys a palladium ring. It has a mass of 5.17 grams and displaces 0.430 cubic centimeters of water. Displaces meaning that it pushes out or takes up that many cubic centimeters of space. Is the ring genuine? And we've got to compare the density of palladium given to us. What are we looking to do here? Any ideas? We've got the volume. So the volume is our 0.430 cubic centimeters of water. That's our volume. We've also got a mass. We're trying to see, is the ring genuine? We could tell one sign that the ring is genuine, one piece of information that would lead us to believe it is genuine, is the density what we expect? Is the density of the ring the same as the density of palladium? That's the question that or the thing that we're thinking about. If the densities are the same, then that's a good indication that it is probably palladium. The ring is probably genuine palladium. If they're different, it's not palladium, or at least it's not pure palladium. So to start, we're going to calculate our density. Density equals mass over volume. So we're going to plug in for our mass, 5.17 grams. And for our volume, 0.430 cm raised to the third power. And the value that we get is 12.02325581. We'd want to round it to 3 significant figures, so 12.0. What are our units? Somebody mumbled it. Grams per cubic centimeter. They just come on through. So grams was on top in our calculation, stays on top. Centimeters to the third was on the bottom, so it stays on the bottom. Is that our answer?
Yes.
We did sig figs, it's 3. What was the question?
Is it genuine?
Is the ring genuine?
No.
If somebody asks you, is this your ID? 5. I'm sorry? Right? The question was, is the ring genuine? This is just a piece of information on our road to figuring out if it's genuine. 12.0, does that match up with 12.01?
I'd say yes.
Yeah, that's pretty close. It's not significantly different. Probably genuine, just based on this one piece of information. For 3 significant figures, these numbers are exactly the same. One of them is a little bit different, but we just didn't measure well enough with our mass and our volume to figure out that they're different, if they are different. Questions? Okay. We can also use density as a conversion factor. So we can use it as a conversion factor between mass and volume. Since density has units of mass and volume. All right, we've got a unit on top, we've got a unit on the bottom, so we can use it to convert. There's 2 ways that I expect that you might do this. One of them is dimensional analysis. We look at the units that we've got. So we've got 68.4 grams, and we've got a density. So looking at the 68.4 grams, we want to figure out a volume. We just multiply or divide by this 1.32 grams per cubic centimeter to get out a unit of volume. The other way that we can use this is like an equation, which is how I expect most of you to use it. So density equals mass over volume. And I'll read the question because I should have read the question first. Example, for a liquid substance with a density of 1.32 grams per cubic centimeter, what volume should be measured to deliver a mass of 68.4 grams? What are we trying to find? Volume. So this, I think I've mentioned before, some questions it feels like they're written backwards. This is an example of a question that feels like it's written backwards. And so this is where finding our question word can be very helpful. So what is our question word? The word what, I'm not asking what's the question word. What is our question word? And the word that's right next to that is volume. So we're actually looking for volume. Volume in our density equals mass over volume is the V. It's on the bottom. There's 2 ways that we can figure out what V is. One of the ways, do algebra to solve for V, meaning we get volume on a side by itself and it's in the numerator. To do that, we can move volume by multiplying both sides by V. This gets the volume to cancel out on the right side. So then we would have volume times density equals mass. And then we need to move our density. So we can move it from the left to the right by dividing both sides by D. We get volume equals mass over density. So that's one way that we can solve for it. This is the way that I'm hoping that we're all capable of doing with confidence. So if we do this, we have mass and we have density. So we can just plug them in and it'll give us our volume. So for our mass, 68.4 grams divided by 1.32 grams per cubic centimeter. Let's peek at our units. We've got grams on top. We've got grams on the bottom. So those cancel out. What happens to the cm to the 3? Where does it end up? On the top or the bottom? It ends up on the top. So it's on the bottom of the bottom. So it's like kind of a double negative. And so this flips up to the top. It's the inverse of an inverse. So we can plug in 68.4 divided by 1.32. We get 51.8. And it looks like 8.1 keeps continuing. We would turn this into 51.8 cm to the 3 cubic centimeters. So that would be our volume. That's the formula approach, or the equation approach. There's another equation approach. So things that have this form of one thing equals another thing over a third thing, we can use this little triangle, this pyramid method that I've seen some students use. So we're going to make a little triangle, a little pyramid. We're going to put density in the bottom left. Mass being on the top of this equals thing is going to go on the top, and volume is going to go on the bottom. The way that we use this is we find the thing that we want. What's the thing that we want in this case?
Volume.
We want volume. So cover volume, and we've got leftover mass over density. So cover V and look at what's left. We get mass over density. So mass over density will give us volume. Notice that that's the same as doing it the algebra way. So if you're not confident in your ability to do algebra, for this type of question, for this type of equation, you can use this trick instead. There's another one that we'll talk about many chapters from now that will work the same way. Questions about either of those approaches? Then there's also the dimensional analysis, the looking at the units way of solving it. And this doesn't require you to do algebra either. So we've got two things that we're given. We've got grams per cubic centimeter. I like to start my problem with the simpler unit. So grams is going to be the simpler unit here. It's just one unit, it's not two units. So starting with 68.4 grams. This 1.32 grams per cubic centimeter, we could rewrite 1.32 grams over centimeters. If we put a 1 in front of that, cubic centimeters, you can always add a 1 for multiplying, dividing. If we add a 1 in there, it looks an awful lot like a conversion factor now, doesn't it? We got one thing with units over a different thing with units. How do we get rid of the grams that we started with this conversion factor?
Put grams on the bottom.
Yeah, we would put the grams on the bottom, the centimeters then would go on the top. So 1.32 grams goes on the bottom, 1 cubic centimeter goes on the top. And now look at what we're doing. We're doing mass divided by density, which is the same thing that our equation would have gotten us. We didn't need the equation. We just looked at the units and said, okay, how do we get rid of the grams and get to the cubic centimeters? So this is the dimensional analysis approach. Just what units do we want to get rid of? What units are we trying to go to? And work things out until we get there. I think that's the better way to do it. There's several many/all equations that you can kind of get away with doing that instead of using the actual equation. Sometimes it's a little confusing though. Questions about any of those three paths? Notice that they all get you to the same point. It's still mass over density. Regardless of which choice you choose, they'll all get you the right answer. So whichever one you like, feel free to use it. All right, when we're using density as a conversion factor, you'll have to be provided the density, because generally we don't just know the density of a thing. Density on exams will be given if you need it like as a conversion factor or to solve for something else. If you're solving for density, obviously I'm not giving it to you because d equals m over v. And for the homework questions for chapter 2, you'll also need some of these density values. You can typically just, for any substance that you can think of, type in on Beyonce's internet, density, the thing that you want, boom, right at the top. It'll tell you what it is. Sometimes it'll be in kilograms per cubic meters. Other times it'll be grams per milliliter, grams per cubic centimeter. All right, we want to calculate density. We've got 30.2 mils of ethyl alcohol. That's the one that you can drink with a mass of this many grams. What's our formula for density? Yeah, D equals M over V. Do we have M? Do we have mass? Yes. Do we have V? Yes, so we can solve. So plug in 23.71002 grams over 30.2 mLs or mils. None of our units cancel, so we're left with grams over milliliters. And we do our division. We get 0.7851. What's the last thing we need to do? Sig figs. How many sig figs should we have in our answer? 3. We're doing division, so we care about the number of significant figures, specifically the fewest. We've got 7 significant figures in our mass. We've got 3 significant figures in our volume. We're going to take the smaller number. We ignore our leading 0. It's just there to help us locate the decimal. We count over to our third number, which is the 5. Look at the 1 to see how we round. 1 says round down, aka just drop it. So 0.785 grams per milliliter. Questions about density? Other important information to know about density: if you've got 2 liquids that are mixed together, let's say that A has a density of 1.00 grams per milliliter. It's probably water. And B has a density of 13.31 grams per milliliter, which is what my brain is telling me the density of mercury is. If we've got those 2 things and we mix them together and they don't mix, if they form separate layers, we mix them in a test tube. Let's assume that we've got a meniscus at the top. And they don't mix, so we've got a heterogeneous mixture, which of those two liquids is going to be on the bottom? The higher density one goes on the bottom. So the higher density sinks to the bottom. The lower density floats on top. That also applies for things like ducks. Ducks are less dense than water, so they float. It's probably other reasons. Wood is oftentimes less dense than water, and so it floats. Ice is less dense than water, so it floats in water. Witches are less dense than water, so they float in water. Monty Python reference. Some of us are less dense than water, and so we float. Maybe you breathe out all of your air and you now sink because you've changed your effective density. So that's some other stuff about density that's important. We'll also do a little bit of stuff with energy. Not a ton, but a little bit. Energy we would define as the capacity to do work, the ability to do work, and we have a definition for work. Work is the result of a force acting over a distance. It has to act over some distance. If you don't move, even if it feels like you're doing work, like if you're pushing on the wall really hard for an hour and the wall doesn't move, technically, since nothing's moved, you haven't done any work. It's a physics definition of work. We won't do a lot with energy or work. We're kind of just mentioning that they exist. Heat is a transfer of energy. Heat is transferred from high temperature to low temperature. Hot things transfer energy to cold things. This is something that we probably mostly know from experience. Just like with mass and matter, we have a law of conservation for energy. So energy is neither created nor destroyed. The amount of energy that we had before something happened is the same as the amount of energy that we had after something happened. We can't create it out of nothing. We can't poof, make it disappear. Nuclear reactions being one exception. So generally, in a system, in a fixed defined area, the total amount of energy is constant. We can change it to a different form. We can transfer it between different things. But it doesn't get created, it doesn't get destroyed. Some types of energy, some of these you'll be familiar with. Kinetic energy is motion energy, movement energy. This chair is a little bit high, but right, wheeling across the classroom. Kinetic energy when I'm moving. Potential energy, there are different types. They're often associated with position, so like height, or composition, so like a spring that you push together. You're giving it potential energy it might release, or a rubber band that you're pulling would be a type of potential energy, or chemical bonds, which shows up later in the slide. We've also got electrical energy. That's the reason that the lights are running and the projector is glowing and all of our devices can do things. That's related to the flow of electrical charge. Thermal energy is like heat. I don't think they're exactly the same. That's just associated with how much the molecules and the atoms are vibrating. So we talked about states of matter. We did talk about states of matter. Okay. Solids, right? We talked about they're touchingly close. They're fixed in their positions. This is kind of like all of us in the classroom, except for me, because I just rolled across. But the rest of us, all right, you're kind of locked in your seat. You're not completely still and motionless, though, right? You're taking notes. You're yawning. You're nodding along. You're checking Snapchat, whatever you're doing. Just like we're doing all of those things, even though we're fixed in our positions, atoms and molecules have random motion. They're moving around in their own little positions in their own little areas, and that's due to thermal energy. We also have chemical potential energy. That's energy stored in bonds. This is where the energy from combustion comes from, for example. So what makes your car go? That's what we're releasing. That's where the energy comes from. It's that chemical potential energy in the chemicals. We're releasing it to form heat and light and other things. An example of a bunch of different types of energy all at once is the Hoover Dam. So the Hoover Dam is a dam. It's a big concrete structure that's blocking water, and this water builds up because it's flowing from a higher elevation point. And so we store up a bunch of water, and then inside of the dam, there are channels, and there's turbines that we can force the water through. The water, because of that potential energy that it has, it wants to flow downhill. We let it flow downhill, and as it flows downhill, we say, hey, you have to turn this turbine for me. And so it turns the turbine. It's using kinetic energy. We're changing the potential energy of the built-up water, turning it into kinetic energy to make the turbine spin, and the turbine spinning generates electricity or electrical energy that then powers homes in the area. That's generally the principle behind dams. All right, now while we're really here, units. We love units. There are units of energy. This is just 4 of them. We've got our SI unit of energy, our metric unit of energy, the joule. I don't know why this J doesn't have its little leg. So we've got the joule. You can also have kilojoules, millijoules, megajoules, gigajoules. Whatever metric prefix you want to put in front of joules, you can do that. And then we've got calories, lowercase c calories. And this is defined as the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius. That's not really that important. Mostly, you should just know there's calories. However, if you look at the next line, what do we have there? It's calories. Wait a second. What do you mean we have calories and then we also have calories? What's different between the two of them? Big C versus little c. So the one that we're used to seeing is the big C, which is 1,000 lowercase c calories or 1 kcal. So this is the one that shows up on the nutrition facts on your foods, on your beverages. And this is capital C calorie. So calorie does not equal calorie. Isn't that fun? I'm pointing this out to you because almost inevitably calories will show up on the exam. And if you get capital C calorie confused with lowercase c calorie, that's a problem. You'll probably get the answer wrong. Okay, so calorie does not equal calorie. Capital versus, or uppercase versus lowercase. So it's super important that you are tracking, is it capital C, is it lowercase c? And then another unit of energy is kilowatt hours. And this is what would be like on an electric meter or on your electric bill. This is, however many cents per kilowatt hour you're paying for. All right, we can do unit conversions with energy. So let's say a large light blue sports drink contains 190 calories. Love the light blue flavor. How many kilojoules is that? What are we given? 190 calories. So we're going to be starting with calories. Is it capital C, lowercase c?
Capital.
Capital. So capital C, cal. What are we finding?
How many kilojoules?
Kilojoules. So we're trying to get to kilojoules. What can we get to, or what can we use to get to kilojoules? Joules. So if we have joules, then we could get to kilojoules because that's a metric prefix conversion. How can we get to joules? Say that again? Lowercase c cal. That's right. So lowercase c cal, we could get to joules. Can we get from big C cal to little c cal in one step?
No.
Yes. So the things that are equal, 1 big C cal equals 1,000 little c cal. For little c cal to joules, we've also got that given to us. 1 lowercase c cal equals 4.184 joules. And then for joules to kilojoules, how many joules are in a kilojoule? What does the kilo prefix stand for? 1,000. So 1 kilojoule is 1,000 joules. Questions about any of those conversion factors or those numbers, those equivalencies? All right, let's get our solution map rocking and rolling. So we've got 190 cal. I'm going to add in a period so that it's 3 significant figures. We want to get from cal to cal. So we're going to put the lowercase c cal on top, the big C cal on the bottom. Because we want to get rid of the big C cal. So capital calories cancel out. That's our first step. Our second step, our 1 lowercase c cal is equal to this many joules. We're trying to get rid of which one? Calories or joules?
Calories.
Calories. Where are we putting calories? On the bottom. So 1 lowercase c cal on the bottom, 4.184 joules on top. Little c cal cancels. Perfect. And then we're trying to get to kilojoules. So we've got 1,000 joules equals 1 kilojoule. We're going to put the 1,000 joules on the bottom. Because we have joules, we're trying to get to kilojoules. So 1 kJ on top. Joules cancels joules. There's another fun thing that we can do to make this easier for ourselves. We've got 1,000 on the top. We've got 1,000 on the bottom. We can also cancel those out to save us a couple of button presses. So we're going to put in 190 times 4.184. Calculator tells us this is 794.96 kilojoules. How many sig figs? 3. So we're looking at the 4 as our last sig fig. Check the 9 that comes after it. This will round up. 795 kilojoules. Questions? Yes?
Can you just write like kilojoules instead of
you could write in, if you wanted to switch this to kcal, yeah, that would work. Kcal is the same as big C cal. Just make sure that you write it as lowercase c cal if you do that. So that's also valid. So the only things here that are new is we haven't seen these units before. And that's kind of it. That's kind of the only thing that's new. It's just new units with different numbers. The process is all the same. The one thing that you should make sure that you know how to do is do these metric prefix conversions. That's the one thing that I expect might trip you up. We've done it before, but it's one thing that I expect might trip you up. The other tricky part being big C cal versus little c cal. All right, part of the reason we talk about energy is because there's a lot of energy that changes hands when we're doing physical and chemical changes. Changes are often, but not always, accompanied by energy changes. So for example, water evaporating, natural gas burning, both involve the change of hands of energy. And the energy that's released during a chemical reaction is it's exactly like the release of energy when a campfire burns. This campfire has some extra colors to it because there's some things that maybe shouldn't have been in there. Systems with high potential energy tend to try to change in a way that lowers their potential energy. So high potential energy wants to change to low potential energy. An example of that with gravity, if I hold my Apple Pencil out and I let go of it, it's got gravitational potential energy because I've lifted it up. What's going to happen? It's going to fall. When it falls, what's happening to its gravitational potential energy? It's decreasing. It's got less until it hits the ground, and then that's as far as it's going to go unless it rolls off something and falls onto something else. So things with high potential energy, like things that are really high, tend to fall. They tend to be unstable. Chemical substances sometimes also have high potential energy. So the famously explosive TNT, trinitrotoluene, tends to undergo rapid chemical changes to lower potential energy. TNT is unstable. It's more unstable than a lot of other things. Like wood is not nearly as unstable as TNT. TNT just goes up in flames like immediately. Wood takes some energy to get it to go. There are also chemicals that are more explosive than TNT that you just leave them out on the countertop and they light on fire. Or you touch it a little too hard and it blows up. Which is always fun to work with. There was one lab that I did in undergrad. It was an upper division lab, and they told us, I think in the lab procedure, hey, just so you know, if you let anything dry out, like if you let some residue dry out in your flask while you're creating this, it makes a contact explosive, so if you just hit it too hard, it could explode. So don't let anything dry out. We were like, oh, okay, very cool. Fortunately, nobody had anything blow up. But that was very exciting. It was a very exciting time. Okay, so the energy change that goes along with physical and chemical changes, we can describe in two ways, depending on which way the energy flows. The first way that it can flow is exothermic reaction. Exo, like outside. So an exothermic reaction, energy is going out. Can anyone think of a word that also has exo in it? Exoskeleton. What is an exoskeleton? What have exoskeletons? Bugs and super soldiers in fake worlds and in the real world. Exoskeletons. Bugs having an exoskeleton, their bony bits are on the outside. We don't have that. We've got our crunchy bits on the inside. So just like that, the heat, this exo, outside, energy is going out. Energy is being lost. There's also endothermic. Endo maybe means inside. So energy is being absorbed. So an example of exothermic is wood or anything else burning. That's the most common example of an exothermic reaction. And then for endothermic reactions, instant ice packs usually have a little thing on the inside that you have to like squeeze it to break. And it's just salt that's in there. The salt mixes with the water, and the way that it mixes, it absorbs energy. And so it rapidly cools down, rapidly absorbs a lot of the energy to do that mixing process. And that's what causes it to be so cold. That also makes them relatively safe in case you accidentally burn it or break it. However, not all endothermic and exothermic processes are straightforward. They might take a little bit of time to think about. So let's finish these examples and then I'll let you out. Thinking about water boiling. For the water to boil, are you putting energy into the water or are you taking energy out of the water? Putting energy into the water. So that would be what? Endothermic. You're putting water in. Sorry, you're putting energy in. Gasoline burning. Is energy coming out or is energy going in? Exo. It's hot. Energy is released. What about ice that forms on a pond? For the ice to form, are you putting energy in or are you taking energy out? You're taking energy out. So this is actually exothermic. So the water loses energy to form ice. And we'll pick up here on Wednesday.